Collision 3, blocks B and C collide. Between these two, there is no spring-like elastic interaction, so when they impact, both bodies will have to dent and deform to some extent. This will most definitely be an inelastic collision. Internal work inside each block will convert kinetic energy into heat as neighboring bits of mass push on each other. So the energy exchanges will be too complex to handle without thermodynamics. So our mathematical analysis will have to be restricted mainly to momentum principles here. Let's do that. If we consider B and C to be a system, two moving objects in this system, then the net external impulse on that system could change the total momentum of the system, but there is no net external impulse during that brief collision. So that's zero, indicating that the x component of B's momentum and the x component of C's momentum will change in an equal and opposite way. Momentum might transfer from B to C or from C to B, but whatever momentum B loses, C gains, and vice versa. We see that the energy of this system is indeed conserved. We could look at that from a pseudo-work point of view. The pseudo-work done on this system by some net external force, but there is no net external force, so the KCM of our block B plus C system would be constant, telling us that the momentum of that system is constant, which we already knew. So a pseudo-work analysis really adds nothing here that we hadn't already concluded. The momentum of the system is conserved since no net external impulse. As for the energy of the system, we could look at the system of B plus C as having a center of mass located somewhere in between them, but we could also consider block B itself, this extended body, as a system. And the center of mass of the system consisting of just block B is located here, center of mass of B. So we could define the KCM for the system consisting of just block B, which would be related to the velocity of the center of mass of block B, which would be related to the momentum, the total momentum of block B. So this is sort of the part of the kinetic energy of B associated with B's momentum. It's definitely not the total kinetic energy of block B, because after all, during the impact in particular, different parts of block B will be moving at different velocities as B crumples or smushes. So, okay, this is just the part of B's kinetic energy associated with its momentum. And it's the part of B's kinetic energy that the pseudo-work energy theorem speaks to. So when B hits C, if B is our system, then the force on B due to C would be an external force changing the KCM of B. So from an energy point of view, both the KCM of B and C could change because the momentum of B and the momentum of C could change, as we saw over here. But whereas the momentum that B loses, C gains, indicating that the momentum of that B plus C system is conserved, the kinetic energy that B might lose could get transferred partially to C, but the kinetic energy that C gained would be less than the kinetic energy that B lost. So in other words, the net change in kinetic energy of our system would have to be negative, as kinetic energy was converted to heat or sound or deformation in that collision. So we would conclude that the energy of the system was not conserved in this inelastic collision. Okay, collision 4. C smacks into the wall. So C here is an extended body. It hits that wall. It's going to have to dent, crumple, deform. This will also be an inelastic collision here. Let's look at the momentum first. The impulse imparted to C by the wall will change the momentum of C. So this is non-zero. We can tell that momentum of C will not be conserved here. C might come to rest when it hits the wall, or it might bounce back a little bit, but definitely not elastically. So the impulse imparted to C by the right wall will be equal to the change in momentum that C experiences. From a pseudo work point of view, we could look at the pseudo work done on C by the wall. So the contact force on C due to the right wall, that I'll be pushing to the left when C hits the wall. We're going to dot that with the displacement of the center of mass of C. So as C hits the wall and sort of crumples, crushes, dents as it moves into the wall somewhat, the center of mass of C will still be moving to the right as C crumples into the wall. So if the displacement of the center of mass of C is to the right, while the contact force on C from the wall is to the left, then the dot product of those two vectors will be negative. The pseudo work done on C by the wall will be negative, indicating that the KCM of the block will decrease. So the momentum of C is not conserved. We can tell that right here due to the external impulse. But the KCM of C, that decreases as well due to this pseudo work here. The loss of KCM, that KCM again would be related to the momentum of C. So as the momentum of C changes, the portion of its kinetic energy associated with its momentum, that's the KCM, that's going to change as well. It will be converted into heat, sound, and deformation. So that is our inelastic collision there, indicating that the energy of our system here is not conserved either. So neither momentum nor energy conserved. Because the energy is not conserved, we call it an inelastic collision. Where did the momentum of C go when it hit the wall? It wasn't destroyed. It was transferred to the wall, which was then transferred to the planet Earth. So the whole Earth gained some momentum to the right in its orbit as a result of this collision, but we don't keep track of that. We just say that momentum of C was not conserved. It was lost from our system here. All right, so looking back, we had 4 collision types, and we can identify what's conserved and what isn't in each case. Between A and the wall here with that spring, we saw energy was conserved, but momentum wasn't. Between A and B, both energy and momentum conserved. Between B and C, just momentum conserved. And between C and the wall, neither energy nor momentum conserved.